these calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.5. Continuity.
Lesson 2. Types of discontinuities and one-sided continuity.
So I have f of x is equal to x minus 1 whenever x is not equal to 3, and it's equal to the output 5 at the single value of x equal to 3. And what I'd like you to do is once again first look at the careful definition, the precise definition of continuity, and start checking the conditions and try to determine whether or not f is continuous at the value x equal 3. So that's sort of your goal, is to answer the question, is f continuous at x equal 3? And remember, that means you have to check those three conditions. You're going to be checking, is f of 3 defined? And if so, what's the value of it? And then you're going to check and see whether the limit as x approaches 3 of f of x exists. And when we go through it together, we'll talk a little bit about how to find that limit. If you have trouble with it, hold on, and once you restart the video, you can check that. If that limit exists, then you'd be checking to determine whether the things, the numbers, the outputs you get in parts 1 and 2 are they equal? Do they match each other? If so, then the function would be continuous at x equal 3. As soon as you find a condition that doesn't hold, you're done, and you don't have to check the other conditions. So take a moment, try that, and see if you can decide whether or not f is continuous at x equal 3, and then we'll go through it together. Okay, well, let's go ahead and see if we can figure out whether f is continuous at 3 using the careful, precise definition of continuity. First of all, is f of 3 defined? Well, let's see. If I plug 3 into this, does the rule tell me how to find an output value? The x value that I'm plugging in is x equal 3, and according to my little rule up here, when x is equal to 3, I'm supposed to use the bottom rule to find the output value. So I'm in this portion of the domain, so f of 3 is equal to, and it's just this constant function, the function 5. So this tells me directly that if x equals 3, then f of x is equal to 5. In other words, f of 3, when we replace the x with a 3, we get an output value of 5. So the answer to this question, is this defined, would be yes, and f of 3 turns out to be equal to the number 5. Okay, in part 2, we're supposed to determine whether the limit as x approaches 3 of f of x exists. Now, this is an overall limit, meaning I'm approaching 3 from both the left and the right-hand sides. Do I have to break it up into a left-hand limit and a right-hand limit as I did in the last example in part B on the previous page? I don't, because this domain for f of x is split up in a very different way. If you remember, the function, I think it was g of x, in part B was defined one way for x less than 3 and another way for x greater than or equal to 3. So it was defined one way for x's to the left of 3 and another way for x's to the right of 3. This is rather different. It's defined as 5 when x equals 3, so for that single x value, but it is defined as this thing, x minus 1, for all other values for any x not equal to 3. That would be to the right of 3 or to the left of 3, anything that isn't equal to 3. So remember, when we're finding the overall limit here, as x approaches 3, we're really saying x is getting closer and closer to 3 from both the right and the left, and the only x that we're not plugging in is 3 itself. And we oftentimes wrote this little not equal sign under our symbol. We're doing the limit as x gets closer and closer to, but never quite equal to 3. So the question becomes, what is f of x for the values of x we are limiting through? And according to our rule, when x is not equal to 3, I'm supposed to use the top rule here. When x isn't equal to 3, f of x is x minus 1. If x were equal to 3, like it is in part 1, x is equal to 5. But for all other values, f of x can be replaced with the top rule, x minus 1. So if I were trying to find this limit, I'd go ahead and say, oh, okay, I'm finding the limit as x approaches 3 of f of x. And for those values, since it's all x's either greater than or less than, but not equal to 3, I can replace the f of x that I see with the top rule. X is not equal to 3, and for those particular values of x, f of x is x minus 1. Notice again I put parentheses around my expression. Now the question becomes, can I find the limit of x minus 1 as x approaches 3? Well, what kind of function is this? It's a polynomial. And remember that a polynomial, we can find its limit by direct substitution. So I just go ahead and I replace the x I see with a 3. I do 3 minus 1 and I get a limit of 2. So we were asking, does the limit as x approaches 3 of f of x exist? And yes, it does exist, and its value is equal to 2. This function satisfies condition 1, f of 3 is defined, and it satisfies condition 2, the limit as x approaches 3 of f of x exists. Now we just have to see if it satisfies condition 3 of our careful definition of continuity. And remember, condition 3 is that the number that we got in part 1 and the number that we got in part 2, or condition 2, those two numbers have to be equal to each other. Are they equal to each other? Well, so we're really asking here, is f of 3 the same thing, I'll put a little question mark here, is that the same thing as the limit as x approaches 3 of f of x? That's really what we're asking in condition 3. Are the things we get in 1 and 2 equal to each other? Well, unfortunately, f of 3 we found was equal to 5. Whereas the limit as x approaches 3 of f of x turned out to be the number 2. And those two things are not equal to each other. Oof. So we've done a lot of work only to conclude that although our function satisfies condition 1 in the definition, it satisfies condition 2 in the definition, it fails condition 3. F of 3 is not the same as the limit as x approaches 3 of f of x. What do we conclude then about our question? Is f continuous at x equals 3? No, it is not. So we would have to say, therefore, f is discontinuous at x equals 3. So it was a lot of work because we happened to have to check all 3 conditions before we got to a condition that didn't hold. Well, let's go ahead and graph this function just so that we can see what's going on graphically and why it is that our function failed to be continuous at x equals 3 from a visual point of view. And to graph this function, notice that whenever x is not equal to 3, I would be graphing f of x equals x minus 1. I'm using the top rule. And if you think about f of x, same thing as y, is equal to x minus 1, that would again be the graph of a straight line, and it's a line that crosses the y-axis, has a y-intercept of -1, and has a slope of 1, or 1 over 1, so I go up 1 and over 1. And so it would look something like this. Let's see. If I didn't have any restriction on my domain, but it only looks like this line when x is not equal to 3. So actually I should put a little hole in the graph here at x equals 3 to indicate the fact that we use that top rule, yeah, for all x values to the right of 3, for all x values to the left of 3, but not at x equal 3. So it would be this line with a hole in the graph corresponding to the x value x equal 3. Well, what happens when x is equal to 3? When x is equal to 3, I'm supposed to get 5 as an output value. In other words, if I thought of it as an ordered pair, x comma y, when x equals 3, the output value, f of x or y, is supposed to be equal to 5. So that would be graphically a single point on my graph. When x equals 3, I get an output value of 5. So I get this dot up here at the point 3, 5. And my graph would look like this. It would be a line that has a hole in the graph right here at the point corresponding to x equal 3. It jumps up to this point at that one value, and then we continue getting outputs by traveling along this straight line. Well, can you see that this function is discontinuous at 3? Yes, it's one of these functions that's discontinuous at 3 because it jumps up at a single point and is redefined at that one single point. One thing I want to mention in the way of just another piece of vocabulary, another piece of terminology, is the idea of what are called removable discontinuities. You notice, yes, this function is discontinuous at 3. But if I went back up to the definition of f of x, we said it's x minus 1 when x is not equal to 3, and it's 5 when x is equal to 3. That's what's giving this point 3, 5 on our graph. If I went back up to the definition, I could actually change this into a new function that is continuous at x equal 3 by changing the definition of f at just one value, at just x equal 3. The problem with the graph is that we have this point right here that we jump up to. Think about what would happen if I were to move this point down, move the dot down, so that it filled in this empty hole here, and we ended up with a nice continuous line or a nice continuous function right through x equal 3. I could just move this one point down. If I could somehow do that, I would end up with a function that is then continuous at 3. So the function as given is not continuous at 3, but we could create a new function that is continuous at 3 by changing the definition slightly. And moving this dot down would be the same as changing the definition of f of x right at x equal 3. And can you see what I would have to change about the output value in order to make this dot move down? This dot is at a height of 5. What height would it have to fill in this empty hole and end up giving me a continuous line right through 3? Well, it looks like the output would have to be equal to 2. If the dot were at 3, 2 instead of 3, 5, it would exactly fill in that hole that we had in the line. So if I redefined f and said instead of when x equals 3 I get an output of 5, if I said when x equals 3 I get an output of 2, I would get a different function, but my new function would actually be a function that's continuous at x equal 3. So let's look at this little note that's at the bottom of the page. It says the discontinuity at x equal 3 could be removed. In other words, we could get a new function that's continuous at x equal 3 by changing the value of f of 3. Remember that value was an output of 5. So by changing the value of f of 3 from 5 to, and what did we say that the output needed to be? We said the output needed to be 2. Notice that means that this would then become a 2, and the number that we get in part 1, condition 1, f of 3 is equal to 2, and the limit was equal to 2, and now these two things would match up. You'd end up having 2 is equal to 2. So you'd have a new function, but you'd have a function that is continuous at x equal 3. if it's possible to do this, if it's possible to remove the discontinuity by simply redefining f at a single x value, at one x value, like we did here, we changed f of 3 from 5 to 2, we call this type of discontinuity a removable discontinuity. And we call it removable if we can take a function that's discontinuous at a particular a value and make it continuous just by changing the value of f at one single x value at the value x equal a, in our case at the value x equal 3. So in this example, our function f of x is discontinuous at x equal 3 if we look at the function as it was originally defined, but we say that it has a removable discontinuity at x equal 3 because we could get rid of it. We could define a new function that is continuous at x equal 3 by changing just that one output value, the output value at x equal 3, and we don't have to change the output value of f at any other value. Well, let's go back to the previous page just for a moment and look at the discontinuities that we found there and decide whether they are also removable discontinuities. And I think that will help you to understand exactly what we mean by a removable discontinuity. If we look at h of x, remember we said that was discontinuous at x equal 3. There was a vertical asymptote right at x equal 3. In fact, the function had no value assigned to it. H of 3 was undefined. And that's why, according to the careful definition of continuity, h was not continuous at x equal 3. Well, the question becomes, is it also a removable discontinuity? Well, that would mean that if we assign a new value to h of x at x equal 3, I should be able to get rid of the discontinuity at x equal 3. So right now h of 3 is undefined. Let's go ahead and give it some value. I don't know, just pick a value like x equal 2, for example. If I went ahead and said, okay, h of x is equal to 1 over x minus 3 when x isn't equal to 3, and I'm going to assign the value 2 when x is equal to 3, I would end up with the point, let's see, the x coordinate is 3, the y coordinate is 2, so I'd end up adding the point 3, 2 onto my graph. Does that make the function continuous at x equal 3? Have we fixed it up? Well, no. If I were to try to draw this graph, it isn't really any more continuous than it used to be. I'd have to draw this red portion. I'd have to jump up, put a solid dot here, lift my pen across up off of the paper again to draw the green portion of the graph, and it would still be discontinuous at x equal 3. So we can't remove the discontinuity by redefining h at just one x value, at just x equal 3. There's no way to do that. And so this particular discontinuity of our original function, h of x equal 1 over x minus 3, is not a removable discontinuity. We say it is a non-removable. It's discontinuous at x equal 3. It's a non-removable discontinuity. Discontinuity. I'll just abbreviate it that way. So we couldn't get rid of the discontinuity just by adding a dot to the graph. That's a simple, intuitive way of saying it. In fact, I'm going to go ahead and erase this dot that's here. This particular type of discontinuity, where the function is going either to positive infinity and or to negative infinity, is referred to as an infinite discontinuity. discontinuity. So I'll put in parentheses that it's a non-removable discontinuity, and the type of discontinuity is an infinite discontinuity. Well, let's look at the example y equal g of x that we had down in part B. The function g was also discontinuous at 3. The question becomes, is that a removable discontinuity? Well, for it to be removable, it means that if we redefine g to have some other value at x equal 3, we can do so in a way that fixes this gap in the function and makes it continuous. But I think you can see that no matter what value I chose to assign to g at 3, if I got rid of this equal bar down here, and I used g of x as x minus 1 when x is less than 3, x plus 1 when x is greater than 3, and then gave g a new value, no matter what value I chose, suppose I chose something like g of 3 equals 3. All that would do would change this to an open circle, and then we would get a new dot right here at the point 3, 3, and the function would still be discontinuous. There's no way in terms of the graph to add one dot or move one dot along the line x equal 3 to make this become a continuous function, to bridge the jump that's between these two chunks of the graph. So again, this would be a non-removable discontinuity, and this particular type of discontinuity where we have a chunk of the graph and then boom, it jumps up and we have another chunk of the graph at a different height is called a jump discontinuity. So this is referred to as a jump discontinuity. Well, let's go ahead and look at one complicated function that has several kinds of discontinuities in it, and we'll get some practice deciding whether a discontinuity is removable or not, and if it is a non-removable discontinuity, whether it's a jump discontinuity or an infinite discontinuity. So let's do that next by going to the page. I guess it's 2 pages from where we just were, since we went backwards a page. So it's this page. We already did this little question that was at the top. It says go back to parts A and B, were these discontinuities at x equal 3 also removable? And we decided that no, they were non-removable discontinuities. One was an infinite discontinuity, and the one in part B was a jump discontinuity. Okay, I'd like us to look at this example. I have one crazy graph here. It's all the graph of a single function, y equal f of x. And what we're going to do is find all of the discontinuities of f, and then we'll classify those discontinuities as removable or not removable, non-removable. And if they are non-removable, we'll try to label what kind of discontinuities they are. So what type of discontinuities do we have at the non-removable discontinuities? So let's just go ahead and look at each discontinuity. Well, if I come in from the left, the first discontinuity occurs here at x equal 5. I can see I'd have to lift my pen off the paper to draw the graph through x equal 5. So the function is definitely discontinuous at x equal 5. So we have a discontinuity here, and I want to go ahead and try to decide, is that a removable discontinuity or is it not a removable discontinuity? Well, to be removable means that I can add one point to the graph at the value x equal 5 and get rid of the discontinuity. I'd actually be creating a new function. It would be different from the function f of x, but I would get a function that then is continuous at x equal 5. Is that possible? Well, it is. I can see that if I just added a dot right here, I guess it would be a dot at the height of 2, so it would be the 0.52. If I just added that in here, it would get rid of my hole that was in the graph. I'd essentially be filling in the hole. and I would get rid of the discontinuity. So there is a discontinuity in my original graph at x equal 5, but we would refer to it as a removable discontinuity. And again, another way of saying this that's a little bit more technical is that if I simply gave f an output value at the input value x equal 5, let's see, I'd want the output value to be 2, that would put the dot right here at an x value of 5 and a y value of 2. If I just redefine my function to have a definition at x equal 5 and gave it an output value of 2, it would get rid of this hole that was in the graph. So by redefining my function at one single x value, namely x equal 5, I get rid of that discontinuity. Okay, let's keep going along here. It looks like x equal 10 is also a place where I have a discontinuity. To draw the graph, I have to draw it going up this way forever, then I lift my pen off the paper to get across this vertical asymptote, and then I would continue drawing the graph on the other side. So there's definitely a break in the graph at x equal 10, so there is a discontinuity there. Is it removable? That means I should be able to add one point to the graph along the line x equal 10, which is actually right along this vertical asymptote, and make the graph continuous. Well, no matter where I add a point, it doesn't matter what height I put in there. Say I put in the point 10, 4, so I put a point that's at a height of 4. It still doesn't make my graph continuous. So there's no way to add a single point into this and to fix it up and make it a continuous function. So this would actually be a non-removable discontinuity. And what type of discontinuity is it if it's non-removable? Notice down here it says what type of discontinuities do we have at the non-removable discontinuities? Well, because this function is going up towards positive infinity on both sides of the asymptote, remember that that type of discontinuity is called an infinite discontinuity. Okay, I want you to go ahead and stop the video for a moment and look at all of the other discontinuities, find where the function fails to be continuous, what x values it's discontinuous at, and then try to classify those as removable or non-removable. If they are non-removable, try to decide if they're an infinite discontinuity or a jump discontinuity. Okay, so hopefully you've had a chance to think about the rest of the discontinuities in this graph on your own. The next place the function is discontinuous would be at x equal 15. I'm going to draw an arrow up here just because I'm running out of room. So x equal 15 is the next discontinuity. I have to lift my pen off the paper to draw the graph through x equal 15. And then we want to also ask the question, is it a removable discontinuity or is it a non-removable discontinuity? To be removable means I can add just one point somewhere along here or move one point somewhere along the line x equal 15 and fix up the graph, make it continuous. Well, the output value of f of x at x equal 15, it looks like it has an output value of 2 because there's a solid dot here. So you notice that right now f of 15 is equal to an output value of 2. Could I change that? In other words, could I move this dot up or down and give it a different y value and fix up this graph so that this part of the curve connects to this part? Well, no, I really can't. Even if I chose a different value for f of 15, such as, I don't know, 4, something like that, that still wouldn't help. That would fill in this hole, but then I would have a hole down here, and the graph would still have a jump in it. So this is a non-removable discontinuity. And what type of discontinuity is it? When the graph has a chunk like this and then jumps down and has another chunk down here. That's right, it is a jump discontinuity. So I'll just put that in parentheses. That's the type of discontinuity we have here. It's non-removable and is referred to as a jump discontinuity. X equal 20, that would be the next place that I can see there's a break in the graph, so that would be the next discontinuity. And again, there's no way to add a single point onto the line x equal 20 anywhere along that line that would make these two halves of the graph match up, and so this is a non-removable discontinuity. And what type of discontinuity is it? Again, because we have a chunk of the graph down here and then another chunk that is at a higher level, we say that the graph has jumped, and this would be a jump discontinuity. Let's look at x equal 25. Again, I'm going to just draw an arrow here because I don't quite have room to fit things in. I can see that there's a discontinuity here. We have to jump up to draw the graph and put this black dot up here and then come back down to the curve. So there's definitely a discontinuity there. Is it a removable discontinuity? Could I move or add a point somewhere along here to essentially fill in this hole and make this function continuous? Well, in this case I could. I could move this one dot down, so I could move this point down and it would fill in the hole. And if I just moved this dot down, got rid of it here and put it right here, I would end up with something that is continuous. I could just draw the graph right through x equal 25 and not have to lift my pen off the paper. So this one is a removable discontinuity. Okay. And what about x equal 30? I can see I have a discontinuity there. I have a hole missing in the curve. And so to draw the graph, I have to pick my pen off of the paper. So there's definitely a discontinuity here. Is it a removable discontinuity? Could I make my function continuous by just adding one point to the graph along the line x equal 30? Well, I could. I could fill in this hole with a point that's right here. Essentially, that would be equivalent to saying that f of 30 is equal to, well, this dot here, it looks like it's at a height of 6. If I made f of 30 equal to 6 and just gave f a definition there, I would have gotten this point right here, and I could draw my graph right through x equal 30 without lifting my pen off the paper. So this would be a removable discontinuity. Okay. We're going to go ahead and look at the next page and talk about a slightly different idea. Just to kind of review what we've done so far, we've talked about the intuitive definition of continuity, that you don't lift your pen off the paper. We have talked about the more precise definition of continuity with the three conditions, and we've learned how to check those three conditions either from the graph or from the equation of the function. And we've talked about different types of discontinuities. We've talked about discontinuities that are removable and ones that are not removable. And of the ones that are not removable, some of them were called infinite discontinuities and some were jump discontinuities. We're now going to look at a slightly different term, which is what are called one-sided continuities, or a function we say is sometimes not continuous at a point, but it is continuous from either the left or the right, and that's referred to as one-sided continuity. So to understand this, I'd like us to look at a specific example, and then on the next page we'll generalize it in a little bit more formal definition. So let's think about this example. It says, consider the function f whose graph is shown. So we have some function here. First, let's answer this question. Is f continuous at x equal 5? Well, no, it's not. I can see that there's a jump discontinuity at x equal 5. So no, it's not continuous at x equal 5. It's discontinuous there. What I'd like us to do is just quickly go through the careful or precise definition of continuity to explain why it's discontinuous there. We can see there's a jump discontinuity in the graph, but let's go through our three conditions. First of all, let's decide whether f of 5 is defined. So I'll ask, is this defined? And let's see, if I plug 5 into this function, is there an output value assigned to it by the graph? Well, I go up to the graph and I go up to where the black dot is, that's where my graph is, and go over to the y-axis, and you notice I get an output value of 6. So yes, f of 5 is defined and it's equal to 6. Second question is the limit, and here we mean the overall limit, as x approaches 5 from both directions of f of x, does that limit exist? Well, in this case, because we have two chunks of graph that are at different levels, to answer the question, does this limit exist, we would usually look at the limit from the left and the limit from the right separately, and if those limits exist and are equal, then the overall limit also exists. So let's think for a moment about the limit as x approaches 5 from the left. That means I'm getting closer and closer to 5 from the left. And as I get closer to 5, it looks like the outputs are collecting around 3. If I look at the limit as x approaches 5 from the right, I'm wondering whether I get the same number. But when I approach 5 from the right, I have to go up to this chunk of the graph and over to the y-axis. And the closer I get to 5 from the right, the closer the outputs appear to be getting to 6, a completely different number. So unfortunately, the limit from the left and the limit from the right don't agree. What does that mean about the overall limit as x approaches 5 of f of x? Well, remember, we said for the overall limit to exist, the one-sided limits have to exist. They do, but they also have to equal each other. They have to agree, and in this case, they do not. So no, the limit as x approaches 5 from both directions of f of x does not exist. So my function fails condition 2 of the definition of continuity, and that's why technically my function is discontinuous at x equal 5. Well, okay, so my function is not continuous at x equal 5. We've decided that. We've even proved it using the careful definition of continuity. However, I would like you to notice the following interesting fact for this particular example. It's true that this overall limit did not exist. However, both of the one-sided limits existed. And an interesting fact is that if we look at the limit from the right side, which we found right here, you notice that the value of that right-hand limit was equal to 6. And what was the value of our function at 5? The value of our function at 5 was also equal to 6. So remember in our third condition in the definition of continuity, the thing that would have to be true for this function to have been continuous at x equal 5 was that this limit would have had to exist, and whatever we got in part 2 would have to equal whatever we got in part 1. For the function to have been continuous at x equal 5, the overall limit as x approaches 5 from both directions of f of x would have to have existed, and it would have had to have equaled the value of the function at 5. Well, we know that doesn't happen in this case. However, the limit from the right exists and equals the value of the function at 5. In terms of the graph, let's see if we can answer this little question. What is it about the graph that makes this true, that makes the limit from the right side be exactly identical to the value of the function when we plug 5 in? Well, remember the limit from the right we got by approaching 5 from the right-hand side, and we said that these values were getting closer and closer to 6. And because there's a solid dot at the end of this right half chunk of the graph, it meant that when we plugged 5 into our function, we go up to the solid dot and we get the output of 6, exactly the same value that the outputs are getting closer to as we approach 5 from the right. So the thing about the graph that made the limit from the right the same number, namely 6, as the value of the function at 5, namely 6, is that this solid dot was at the end of the right-hand chunk of my graph. If you look at this part of the graph where there is an open circle, well, then the limit from the left was equal to 3, whereas the value of the function was equal to something entirely different, namely 6. So what about the graph makes this true? I'll just put down here that there's a solid dot on the right chunk of graph. And because it's on the right chunk of graph, that means the limit as x approaches 5 from the right is going to agree with the value of the function at 5. When this happens, we say that f is continuous. Well, we know it's discontinuous at 5, but when this happens, we say that f is continuous from the right at x equal 5. So it's not continuous at 5, but it is continuous from the right at x equal 5. Let me go ahead and erase this purple line that I put in here so that we can see the original graph again a little bit better. So here's my graph. We had this chunk with an open circle and then this chunk with the closed dot, meaning that's the point on the graph corresponding to x equal 5. And if all this seems rather complicated, probably the only thing you need to remember is just how to determine from the graph whether something is continuous from the right. And the way to determine from the graph that this is continuous from the right is whether or not the solid dot is on the right chunk of graph. So we would say this function is not continuous at 5, but it is continuous from the right at 5 because this right-hand chunk contains a solid dot. This particular graph would not be continuous from the left at 5 because we have an open hole in the graph, an open circle here on the left chunk of graph. Let's go ahead and look at these definitions in a formal setting, and then we'll learn and get a little bit more practice just deciding whether a function is continuous from the right or from the left at particular x values. And I think once we get a little more practice and see another example, this idea will make more sense to you. Okay, so here's the formal definition. We say f is continuous from the right at a number a. And here's a picture. It looks very similar to the one we just saw. We're looking now at a particular number a on the x-axis. And notice that this is like the example that we saw before. The right chunk of graph has the solid dot at the end. The left chunk of graph has an open circle. So this is an example where it is going to be continuous from the right. But let's write down technically what that means about the function. Just like we said on the last page, it will be continuous from the right at a if the limit as x approaches a from the right of f of x agrees with the value of the function at a. In other words, if that equals the same number you get when you plug a into the function. So when we write this statement, remember we're assuming the limit from the right exists. We're assuming that f is defined at a, and then we're saying those two things end up being equal to each other. It's a weaker condition than saying that the function is continuous at a. To say the function is continuous at a, the overall limit as x approaches a from both directions of f of x would have to equal f of a. But we are only specifying that the limit as x approaches a from the right of f of x agrees with f of a. And that will get this solid dot to be right here on the right half chunk of the graph. As I get close to a from the right, the output values are collecting around the same value I'd get if I plugged a into the function. And a very similar definition for continuity from the left-hand side. If you look at the picture right here, you notice that the solid dot is at the end of the left chunk of graph. And so in that case, we will say that f is continuous from the left at the number a. Again, it's discontinuous at a. There's a jump discontinuity there, but we will still say it's continuous from the left side as long as this solid dot is at the end of the chunk of graph that we see coming in from the left. Let's see, what do you think we would have as our technical definition here of continuity from the left? Well, to get this solid dot to be right at the end of the left half chunk, what we would need to have happen is that the limit as x approaches a, from which direction? From the left of f of x. That would have to exist and agree with what we get when we plug a into the function. So the limit as x approaches a from the left of f of x would have to equal f of a. And again, the idea is that if the limit from the left, as we get closer and closer to a from the left, these values are getting closer and closer to some number, maybe call that L. Well, if that agrees with the value when we plug a into the function, if we also get L as an output value, then this dot right here will be at the end of this chunk, left-hand chunk of graph, and we will have a graph that is continuous from the left at A. All right, let's go ahead and look at another example where we're just going to get used to deciding whether a function, if it's discontinuous at a point, if perhaps it is continuous from the left, maybe it's continuous from the right, or maybe it's not continuous from the left or from the right. So in this example, at each discontinuity, we're going to determine if f is at least continuous from the right, or if it might be continuous from the left, or sometimes it might be neither of those. It may not be continuous from the left or right. Okay, so as we come in from the left here, what's the first x value at which this function is discontinuous? The first place it's discontinuous is at x equal 5. So we know our function is discontinuous at x equal 5. Now we want to ask, is it at least continuous from the right, or perhaps from the left, or maybe it's not continuous from the right or the left? Well, as I look at this discontinuity, I can see that the left-hand chunk of graph contains the solid dot. And so this function will be continuous from the left. So this is a function that's discontinuous at x equal 5, but it is continuous from the left. And that's because my solid dot is on the left hand, at the end of the left-hand chunk of graph. If you want to check it very technically, you can go ahead and look at the limit from the left, and you notice that if you put in values that are to the left of 5, go up to the graph and over, it looks to me as if the limit from the left, the outputs are collecting around 4. So the limit as x approaches 5 from the left of this function, I'll call it f of x, is equal to 4. Now let's go ahead and actually plug 5 into this function. And if I plug 5 into this function, I go up, here's the solid dot, so that tells me right there, I go over, and I get an output value of 4. So f of 5 is also equal to 4. So the limit as x approaches 5 from the left of f of x is equal to the value of the function at 5. They're both equal to 4. And so that would be a way of using this definition that we have here in a more technical sense to prove, yes, this function is continuous from the left at 5. But in terms of the graph, you can just look and see whether or not this left chunk of the graph contains or has a solid dot at the end, meaning that the point is right here, and then you can say, ah, yeah, that's continuous from the left at x equal 5. Okay, let's look at x equal 10. I can see I have a jump discontinuity at x equal 10, so my function is discontinuous at 10. Is it continuous from the left, or perhaps from the right, or perhaps neither of those? I'd like you to stop the video and think about the discontinuity at 10. There's another discontinuity at 15 and also at 20. And in each of those cases, we know the function has a discontinuity there at 10, 15, and 20. But try to decide if the function is still at least continuous from the left or perhaps from the right, or maybe it's not continuous from the left or the right. So take a moment to do that, and then we'll go ahead and go through it together. Okay, so for x equal 10, I can see I have a jump discontinuity, and I can see that the solid dot is on the right chunk of graph. And so this would be a function that's not continuous at 10, but it is continuous from the right. Sorry, my pen does not want to stay written for some reason. So this function is continuous from the right because the right chunk of graph contains a solid dot here. It is not continuous from the left because we have an open circle here. Sometimes I have students say, well, what if I had a solid dot on the left chunk as well? Then wouldn't it be continuous from both the right and the left? But that wouldn't be possible, because if I had a solid dot here, I actually wouldn't have the graph of a function. Remember, the graph of a function has to pass the vertical line test. Every input has to correspond to just one output. And if I had a solid dot right here on the left chunk as well, and I drew a vertical line right through x equal 10, I would actually have two output values corresponding to the input value x equal 10, and that can't happen for a function. A function is a relation between x and y for which every input value goes to just one output value, so that occurrence wouldn't come up. Okay, how about x equal 15? It looks like we have an infinite discontinuity at 15. Is it continuous, say, from the left? That would mean that there would have to be a solid endpoint value when I get to x equal 15. But you notice that this function, let's give it a name, we'll call it f of x, this function is not even defined at 15. There is no point on the graph corresponding to x equal 15. So there's no solid dot like there is here. F of 10 is defined and has an output value of 2. There's no value for f of 15. The function is undefined at x equal 15. So no, this left-hand chunk of the graph does not have a solid dot anywhere along the line x equal 15, and by the same token, the right chunk of the graph doesn't have a solid dot at the end of it either. So the function is discontinuous at x equal 15, and it's not continuous from the right or from the left. So I would have to say neither. In other words, this function is not continuous from the right, it's not continuous from the left, it's just discontinuous at x equal 15. Okay, let's look at x equal 20, another jump discontinuity, and again we'll try to decide, is it continuous from the left, and we'll look at continuity from the right, or perhaps it's neither of those. Well, to be continuous from the left, as I come in from the left, I would need to have a solid dot here at 20. That way the limit from the left would agree with the value of the function at 20. But there's an open circle here, not a solid dot, and so it is not continuous from the left. If it were to be continuous from the right, then this right chunk of graph would have to have a solid dot at the end. That way the limit from the right would agree with the value of the function at x equal 20. In fact, this function is undefined at 20. You notice that if I tried to find the output corresponding to x equal 20, well, I go through this hole in the graph, I go through this hole, and I never hit the black graph. So f of 20 is undefined, just like f of 15 was undefined. There's no point on the graph corresponding to x equal 15. There's no point on the graph corresponding to x equal 20. So the left chunk doesn't have a solid dot, the right chunk doesn't have a solid dot, and so this function is discontinuous at 20, and it is not continuous from the left at 20, it's not continuous from the right at 20, so it's, in answer to this question, we would have to say neither.